And also, like if on
Do I need to share the screen from?
yes, yeah, share screen. And if people online they want to unmute and ask a question, they should be
Okay.
able to as well.
Okay. Yeah, I do.
Yeah, see it.
So, broadly speaking, the goal is
Great.
to get ideally just one data set where something.
All right, yep, looks good. You want to test if I think your microphone is working. I think I heard you coming through.
Can you hear me?
Yeah,
So. This is like.
I'm actually hearing you things. Oh, no, that is easy. Okay. Yeah, cool.
All
All right. Excellent.
Okay, thanks.
I think we're all set.
Yeah, I have my phone with me. So. Okay.
Those are. Even you have the most flexible factor, right?
Do you need microphone or
Yeah, I can use my phone.
so mic?
Here, it's not right next to each other, like right in front.
Yeah.
But what I see here, that mostly. And this gets really complicated.
So
Everyone is there.
because you don't have anything at the bottom.
Oh, no.
That should be fine.
Okay, yeah. Sure. Okay.
Yeah, I'll introduce you maybe in 1 minute.
Yeah, sure.
That's what I see.
给人听不好放那个，就觉得比较开心。谢谢，到时候有空来聊。就不用。对对对，有时间可以玩。以前就一有时间就来找我。Hi everyone, welcome to the first seminar of the quarter, and it's my pleasure to introduce Dr. Jing. Dr. Jing is assistant professor at UW Econ and also adjunct professor at statistics. And she has done a lot of interesting works in the causal inference of high dimensional data, semi-parametric models, and partial identifications. And she graduated in 2015 from economics at University of Wisconsin-Madison, so the same badger as I am. And yeah, so without further ado, the floor is all yours.
Thank you so much, Tim. Yeah. Excuse me. It's my great pleasure to be here. Thank you so much for coming today. So today I'm gonna talk about some work I've been working on about estimation and inference for heterogeneous treatment effects for observational data with high dimensional covariance. In particular, I'm gonna talk about 2 projects I'm working on about quantile treatment effects for observational data with high dimensional covariance. So let me just quickly do an introduction about the heterogeneous or conditional quantile treatment effects I'm interested in. So quickly introduce the notation here. So when I talk about the heterogeneous quantile treatment effects, I mean the conditional quantile treatment effects. So they are equivalent in my definition. And we think for causal inference with observational data, this is a very interesting parameter. That is So mathematically, it is defined as the quantile of the difference of the potential outcome y1 minus yd conditional on the treatment and the covariance x. So y1 and yd are, as I think all of you know, is the potential outcomes indexed by a binary treatment variable d, and x is a vector of covariance. So in my setup, the x can be very high dimensional. So the dimension of x can be much bigger than the sample size, okay? And one thing I'm particularly interested in as a econometrician, so is I'm interested in like observational data. When I say observational data, I mean the treatment in my setup is not exogenous. I'm not working on this random assignment for the treatment. Instead, I'm working on the case when the treatment variable is endogenous. So a leading example in economics or social science particularly is, say, the potential outcome. The Y could be, say, wage rate, and D is the participation of a job training program. So in this case, the treatment variable D is binary, whether a worker participates in a specific job training program or not, okay? But in the observational data, this assignment is not random, okay? People have these self-selected problems. So they say the reason some people prefer to participate in a job training program is because they think the job training program can help them to increase their wage. So the potential outcome the treatment is like a self-selected one. It is not randomly assigned. And usually in this case, we need to have a binary instrument variable denoted as Z to identify the conditional quantile treatment effect, okay? So a leading example here is the Oregon health insurance experiment, okay? So this health insurance experiment was conducted in 2008. And the idea is because we really want to know whether Medicaid has any impact on a person's health outcome or not, okay? But of course, we also know only those people, if we just ask them to voluntarily take the Medicaid program, only those people who need the Medicaid or have any medical needs will participate in the program. So then the treatment, whether a person has Medicaid or not, can be regarded as endogenous. The idea here is then in this experiment, we say, okay, why don't we just run a lottery? Only those people who win the lottery can get the Medicaid, okay? And then we can study the effect of Medicaid on some health outcomes. So in this experiment, the instrument variable Z is lottery, whether a person wins a lottery or not. This is a binary treatment variable. Sorry, this is a binary instrument variable. And the endogenous variable is D, that is whether a person has Medicaid or not. And we're interested in some health outcomes, like the family income, the health status of the person, the mental health status of the person, or maybe some other health outcomes. So we really want to know whether Medicaid has any impact on individuals' health outcomes or not. But in this case, we believe Medicaid is endogenous. So we have an IV called lottery to help us to identify the effect of the treatments on the potential outcomes. So to summarize, the notation I'm going to use for today is I have a binary treatment D is equal to either 0 or 1. And I have a binary IV, so my instrument variable Z is also equal to 0 or 1. Then well-known results in the literature is then we can just kind of divide the data into 4 subgroups, okay? So the first group is called compliers. This is the group of people when the IV say if the person wins the lottery, for sure, she's gonna participate in the Medicaid program. So this is the group of the people when Z is 1, then the treatment D is 1. And when Z is 0, then D is 0. Okay, so we call this is a group called compliers. And we have a second group. This is the group that when the lottery is won, but the person refused to participate in the Medicaid program. So this is the defiers, and we're not interested in this group. And we also have like a always takers, the group of always takers. It means no matter whether the lottery is 0 or 1, this person is always gonna buy Medicaid. Of course, like in the Oregon Health experiment, we don't observe this group because only those people who win the lottery can get Medicaid, okay? But in general, in a very general framework, we also define some people called always takers. And the last group of people is called never takers. So this is the group, no matter you win the lottery or not, they refuse to take the Medicaid, okay? And a well-known result is that in the literature, we all know if the treatment variable is endogenous and we really need the IV to identify the treatment effects, then we can only point identify the average treatment effects and the quantile treatment effects for the compliers. So people call this is the local average treatment effects and the local quantile treatment effects. When they say local, they mean we only can point identify the treatment effects for the compliers. Okay. And sometimes people say we're also interested in the local conditional average treatment effects. When they say that, they mean they are not only interested in the average treatment effect or the local average treatment effects, they're interested in the local average treatment effects conditional on covariance. So I'm gonna give rigorous definition in a second, okay? And also they're interested in the local conditional quantile treatment effects. When they say that, they mean they are interested in the quantile treatment effects conditional on covariance for the complier group. Okay, so today I'm going to talk about 2 papers I'm working on. So the first one is I'm going to talk about how to do uniform inference for local conditional quantile treatment effects curve with high dimensional covariance. And in the second project, if I have time, I'm going to quickly discuss like if I believe the compliers also have self-selection problem, then how can I still, no, I cannot point identify the local conditional quantile treatment effects, but still I can find some sharp bounds for the local average treatment effects and the local conditional treatment effects. Yes.
Just a quick question. So in your Oregon study, you would assume there's no defier nor always.
I assume there's always taker, but we don't. So, sorry. I assume there is defier. So those people who win the lottery, they may not go to the Medicaid. They still may not buy the Medicaid.
But is the lottery eligibility?
Yes.
But
So how could they defy?
yeah, how could
Could they steal
how could
Medicaid if
buy
they-
Medicaid if they don't win the lottery?
Oh, if they win the lottery, they can still choose not to buy the
But
Medicaid.
what about the other?
Oh, the other one is not, yeah, is not observed.
So you would assume the population would not have any decline. So if they don't win the lottery, they wouldn't even be eligible to buy.
But if they win the lottery, they still cannot choose not to buy.
I guess how is a defier functionally different than a never taker?
In the Oregon?
Yeah,
Oh, in the Oregon model or in general?
in this Oregon case.
Oh, in this Oregon case, no.
Okay, because like the defiers and the
That's
never
right.
takers
Yeah, yeah.
differ only in like an impossible
right.
condition.
Yes, exactly, right. But in general, we can still distinguish this.
Okay.
But does that imply in Oregon study, you would assume there was no defier?
Or we say, in the Oregon case, we say, we cannot distinguish the defiers and the never takers.
And you similarly can't distinguish the always takers from the defiers.
That's
correct?
right, yes. Mhm. Yeah. But this is just one example, but in the general framework, talk, we're still just trying to define this into 4 groups. Yeah. Okay. So, yeah, so what if the first problem that has been solved is like, what if we are just interested in the conditional local average treatment effects, conditional high dimensional X? So this is generated from the very classical Angrist-Rubin's model for the local average treatment effects. So here we say, instead of considering the unconditional one, we are considering the one conditional on high dimensional X. And we say in this case, I've done some earlier work like talk about how to do estimation and inference when X is high dimensional. Okay, so this is not the interesting case I'm going to talk about today. The one I'm interested in today is what if I'm interested in the local quantile treatment effects, but conditional on this axis. Okay, so and this axis is high dimensional. Like in Oregon Health experiment case, we actually have a very long list of covariance about these participants. And so, of course, the conditional quantile treatment effects can be defined, can be generated from the conditional distribution of the potential outcomes, conditional on the treatment variable D and X, and also for the complier group, D1 is bigger than D0, okay? And it can be shown just like the average treatment effects for the compliers, for the local quantile treatment effects for the compliers, we can still write down the conditional distribution for the complier group based on the information we get from the instruments. So we can still write this conditional distribution as the ratio of the differences for the expectation of the indicator function conditional on high dimensional variable X, and also some instrument variable Z. Okay, so Z is either 1 or 0. And we can define the conditional distribution for the Y0 similarly. Okay, sorry, there should be an X here. Okay. And then we can invert these 2 distributions to get the local quantile treatment effects, conditional on D and X. Okay. So if you look at this, then you may say, okay, probably then what is the way to estimate the local quantile treatment effects? Can we just directly probably estimate these 4 conditional expectation and then take the difference and then take the ratio? Probably then we can still estimate the conditional distribution first and then invert it to estimate the conditional quantile. Okay, that is, yes.
So can you clarify how FY1 and FY0 are different? Like conceptually, what is FY1?
FY1 is the distribution of the potential outcome for the when D is equal to 1.
Okay.
And Y0 is the one when D is equal to 0.
Okay. Oh, that's what you're multiplying. Okay.
Yeah. Okay. So that is one way to go. But if we do that, you're going to see if we do estimation query, that's fine when X is high dimensional. But if you do inference, there are some technical challenges discussed in the literature that it is really hard to estimate you can think about this, right? When X is high dimensional, then you have to estimate 4 high dimensional conditional mean and then take the difference and the ratio. So probably this is not the efficient approach to go. So in the literature, then what people do is to take a slightly different approach I'm going to discuss next, okay? But before that, yes.
Sorry, can I ask a question about the definition for quantile treatment effect?
Yes.
So here it seems that quantile treatment effect is defined as the difference between the quantile of the distribution of Y1 minus Y0.
Right.
Like, but it's not the same as the quantile of the distribution of Y1 minus Y0, right? Like,
right. Yeah. So
Just follow up on that. So at the start of the talk, if I remember correctly, you define the local effect as the quantile, the difference to quantile.
I think I defined in this y1 minus conditional x minus, yeah,
You go to your slide 1.
you mean? Oh, you mean this one?
Seems like it's
Sorry,
Y1
yeah. So this, yeah, so I need to clarify, this is the one I'm interested in, but in practice, I can only define the quantile treatment effects in that way, yes, without any stronger assumptions. So there is a way to convert these two, but I need also, yeah, but I need some stronger assumptions, yeah.
Point.
This is not point identified. The thing I should clarify, the thing that is point identified is this one. Okay, yeah. That's a good question, yeah. So yeah, maybe I just wanna be clear, like what is the parameter of interest in my case? So in this case, for a given quantile and some covariant x, I'm interested in the local conditional quantile treatment effects on the compiler group. So this is defined as the difference of the quantile, sorry, the difference of the quantile function conditional x for the compiler group. And also I'm interested in the local quantile treatment effect, that is the expectation of the difference of the two, okay? So for estimation and inference, the causal parameters of interest is the first one is gonna be the local quantile treatment effects. So this is the one that taking the expectation over x. We are interested in the local quantile treatment effects for a given quantile and also the local quantile treatment effects curve that's gonna changing with respect to the tau over a range of the taus, the quantiles. That's the first parameter of interest. The second parameter of interest will be the covariant effect. That is the derivative of this local quantile treatment effect with respect to some specific covariant xj. And also I'm interested in the one that is the local conditional quantile treatment effects. So this is the one without taking the expectation. Okay, so this is the one is a function of x. So I'm interested in, for this one, I'm interested in how to do estimation and inference for the local conditional quantile treatment effects for a fixed tau and x, as well as the curve at some x, but uniformly over a range of tau. Okay, so that are the causal parameters of interest. Any question? So let me quickly talk about identification, point identification, okay? How can I get point identification? This is not our contribution. This is well known in the literature. We need 4 types of assumptions for point identification for both the local average treatment effects and the local quantile treatment effects, as well as the local conditional average treatment effects and the local conditional quantile treatment effects. The first one is the independence, okay? So we see with the help of the IVZ, then we say conditional on X, then all the potential outcomes. So if I index by this by Y00, the first index is D and the second one is Z. Okay, so have binary treatment and binary IV. So these all the potential outcomes indexed by the binary treatment and the binary Z is going, and as well as the DZ and D1. So DZ is the treatment when Z is 0 and D1 is the treatment when Z is 1. All of these is going to be independent with the IV conditional X. Think about Z as lottery. So apparently this holds for the lottery case. And the second one is the exclusion restriction. The third one is about the first stage, the support of the first stage. And the last one is monotonicity. Okay, so probably the most controversial one is the last one, monotonicity. This one is to say the probability of D1 is bigger than D0, conditional X is going to be 1. Okay. So these four are all pretty standard assumptions for identification in the literature, and we're just following these assumptions. And the key idea here is for identification. So this is from a very old paper by Abadi, Angrist, and Inference. This is to say, how can we identify the local quantile treatment effects? And how can we identify the local conditional quantile treatment effects? The way to do is probably I talk about one way to do is to start from the conditional distribution and then take the difference and the ratio. Alternatively, maybe we can just think about this in a slightly different way. This is to say, we can, if we just model the conditional, local conditional treatment effects, this omega, by some parameters I called theta, okay, as a linear combination of x and theta, then I can actually identify the local conditional quantile treatment effects is equivalent to identify the parameter I call theta 0. And then how can we identify the theta 0? That is to say, we can first of all define a standard way, define a check function. And then I just want to minimize the expectation of this check function condition on the compliers. So this is just like a quantile regression, but the difference here is I only focus on the one for the complier group. So D1 is bigger than D0 is the complier group, okay? So maybe I can just run a conditional version of the quantile function to get my theta 0 and show my theta 0 is unique. So I can identify the theta 0 from this objective function. Okay. So this is what they argued. And they say actually because we're conditional on these compliers equivalently, what we can do is to show this equation 2 is equivalent to a minimization problem that is unconditional, but we need to put a weight we call kappa function in the objective function. So then this theta 0 tau is also the argmin of the expectation of something we call a kappa function times the check function y minus w. Okay, and what is this kappa function? This kappa function is a combination of the propensity score, but not for the treatment variable. It is for the IV. Okay, so this is kappa function is generated from the propensity IV function. Okay, so when z, it is a function of the treatment variable d, the IV z, and also the conditional probability of z conditional on x. So they say based on the 4 assumptions I just listed, then the parameters theta 0 can be point identified the theta 0 is the unique solution for equation 3, the minimization problem 3. And then as long as we can find a sample analog of this, we can just find a solution of theta 0 for a given quantile point tau. Okay. So this is their argument. But in practice, the problem is, okay, so maybe you think, oh, then this seems to be an easy problem to solve. We just need to estimate this kappa function first, right? And then plug in the kappa function to the objective function and then run a quantile regression, a linear quantile regression. That might be the way to go. But in practice, the challenging problem here is what if the X is high dimensional? And that's, so that's what we think, okay, right? So very natural way to do is, okay, it is okay when X is high dimensional. We do have some very standard way to do to estimate the conditional probability function, just run a lasso, for example, and then plug in this to get kappa. So that's what we can do. Okay, so for example, the first step is to estimate the kappa by lasso and call the estimator kappa tilde, and plug in kappa tilde to the sample analog of the second stage quantile regression model, and run a penalized lasso, right? So this seems to be standard. But in practice, this actually is a pretty challenging problem. The reason is this kappa, the sample analog of the kappa, is not positive. So even though the population one is always positive, the sample one, the can be negative. So actually, if you think about the objective function here, the loss function is not convex. So it is a non-convex loss function. And we need to consider a restricted loss. So by restricting the theta to be to inside a bowl, then we can run this regression. Okay, so that's the main challenges here. So for estimation and inference, the first challenging is when we think about the second stage estimator, the objective function, because the kappa tilde can be negative, so the objective function is non-convex. And also it is non-smooth because we're running a quantile regression. And the second challenging here is if we want to think about how to do inference, I need to correct the bias from the first stage, as well as the bias by running a high-dimensional quantile regression in the second stage. So that are the two main challenges we faced. Okay, so to solve the first challenge, how to run loss function that is non-smooth and non-convex. In the paper, we propose a new algorithm. We call this is linear programming with linear complementary. Okay, so because we have some additional constraints there, so we say if we just use this new algorithm, then we guarantee the convergence of the solution to a local optimum. And we show the minimizer, local minimizer, is going to be a consistent estimator for the true parameter of interest. Okay, so this can be regarded as a mixed integral linear program problem. And due to the time constraint, I will not talk about consistency and rate of convergence, but I'm going to quickly go through how we construct the bias estimator based on the two-step estimation and show how to do uniform inference for these local conditional quantile training effects. Okay. So before that, let me pause here to see if any question. Yes.
Yeah, maybe, I don't know if I have time to go through this, but you said because it's non-convex and non-smooth, so we put some constraints, and so is it easy to explain intuitively what that is?
Maybe I can talk to you after, the talk, yeah, because I think it's pretty standard to solve the problem. So maybe just quickly talk about this here. Without this negative kappa I, we don't have to solve this constraint problem. Then this is if all the kappa i's are positive, then this is a two-stage quantile regression with some parallelization and one conjugation. So for that one, I think we have some standard package to run, but we have to take into the consideration of the planning estimator in the width. So as long as you consider that, take that into consideration, then it's quite standard. So the challenging here is, of course, this is one way of the solution. There might be some other ways to solve this problem. Any suggestions are welcome. But here, what we do is we just restrict the data, the parameter space in a bowl. Okay. And we allow the bowl to grow with the same size. So then there's an additional constraint to write down the Lagrange multiplier. So it requires a new algorithm.
Okay, so is that saying like as long as we restrict the parameter to be within Rn, then there must be a unique solution with this constraint?
We don't know about the global solution. We just know there's a local
solution within the
constraints. Okay. And show the local solution is going to converge to the true parameter of interest.
Okay, thanks.
But there might be some other way to do it. Yeah. In the literature, there are some people like this in the last literature. People do talk about like how to solve constraint minimization problem if they have like a non-convex problem, but we don't find paper talking about quantile regression case. So in our case, there are two things that are new. First of all, we have this plugin estimator, and then we also have like not only non-convex but also non-smooth objective function to estimate the quantile treatment. So, yeah.
Thank you.
Yeah, thanks. Yeah.
I can just clarify.
Yeah.
that If you instead constrained your first step to learn a kappa tilde such that you didn't violate this negativity constraint, would you then be able to do something more vanilla in stage 2?
That's possible too.
Right, 'cause
So
as you said, like, so
right.
like the kappas, right, like the population quantities, like,
Right,
like,
so you
should be
can
not
do
negative,
some, you
right?
should do some trimming. But then you have to take into the consideration of the trimming in the second stage objective function. We try that, but we find it's actually more complicated probably.
Well,
And
the-
also you can do like projection, approach, but
Okay,
it's gonna complicate the inference procedure. So, but that might be a way to go. But let me just explain how we do inference. So maybe you can see why the trimming or the projection might be, might complicate this. But that's a good suggestion.
well, just to be clear, right, like the projection and the trimming are like algorithmic implementations to solve a constraint problem.
Right,
Like if you could directly solve the constraint problem,
right.
you wouldn't necessarily get this propagation, but it's more the like these post hoc ways of projecting the solution
Right.
cause problems.
Because when you do the projection, you also have to consider X is high dimensional. So for estimation, I think that's totally fine. For inference, it's gonna make the bias correction more complicated. Okay, so I have like 15 minutes, so maybe let me just quickly go through the way we do the debias. Okay, so what do we do for debiasing? Everybody here knows how to do debiasing, so let me just quickly go through the basic idea here is, okay, we're gonna start from, since my X is high dimensional, so I'm going to define W as the combination of X and the treatment D. Okay, so the W can be general, it can be dx, or it can be dx and the interaction term of D and X. Okay, so then when my X is high dimensional, my D is also high dimensional. And in that case, a well-known result here is when this X is high dimensional, apparently, even though the population one, the M matrix, which is the gram matrix for the second stage, just like the Hessian matrix for the quantile regression, this one, the population one can be inverted, the sample one cannot, when the dimension of X is bigger than the sample size. So what we do here is we're just running a linear program. It's called climb, and to estimate this, the inverse of the M matrix. Okay, so this is pretty standard. Nothing is new to estimate the matrix. There are many ways to estimate the matrix when the matrix is high dimensional, but that's what we do. And then we need to correct the bias from the first stage and also as well as the second stage. So what we do here is, if you think about the debiased estimator, so let me just explain what's going on in the debiased estimator. So the debiased estimator is constructed by the lasso estimator from both stages. In the first stage, as I just mentioned, I have a kappa tilde. The kappa tilde has a parameter that is gamma tilde. So my constraint quantile regression from the second stage gives me something called theta tilde. Okay, so this is the lasso estimator from the second stage. And I have a gamma tilde. This is the lasso estimator from the first stage for the kappa function. And also can construct a debiased estimator for the gamma tilde from the first stage for the lasso estimator. So you can see, that's why I find the trimming or the projection is complicated, because if I have a trimming or like a projection, it's not clear what is the bias correction estimator for the first stage. So if we don't do that, then I can just use a standard bias correction estimator I call gamma hat. Okay, so this is the gamma hat term. And so the biased estimator is constructed by the lasso estimator minus the B matrix, the inverse of the Gram matrix or the Hazen matrix for the quantile regression. So this is the B hat, which is also have to index by the theta tilde and gamma tilde times. This is like the inference function from the second stage quantile regression. And this, if I don't have the first stage, then my bias estimator is going to be theta tilde minus B hat times the sample analog of this. But because I have a first stage, so I also need to have a second term. And in the second term, I have this B hat, as well as a consistent estimator of the covariance about the covariance of the first stage and the second stage. So with all of this is how we construct the debiased estimator. Okay, for the two-stage quantile regression with a plug-in estimator from the first stage, that's what we do. Okay, so then we can show for the covariance, then we can show we can construct the, after we construct the biased estimator, all the thing left is tedious but relatively standard. We just need to construct the simultaneous confidence bands for this theta for each covariance uniformly over tau. And we can show, as long as we can find the inference function for the debiased estimator, then we can construct a Gaussian process to approximate the symptotic distribution of the quantile process for each J. Okay, and then use Bootstrap to construct the uniform confidence bands uniformly over tau for this each covariance theta. And also similarly, I can construct this for the local conditional quantile treatment effects curve. Okay, so this is going to be the linear combination of the theta as well as this axis. In particular, we consider the case when the covariance X can be dense. So in the sense that if we look at the local conditional quantile treatment effects, we allow this linear combination W to be dense, so they don't have to be sparse. We don't have to restrict the L1 norm to be bounded, but still we can find a regularization estimator to estimate the combination of the B matrix and the dense covariance W, okay, and show we can construct an inference function and valid bootstrap methods to find the confidence bands for the linear combination of the W and the theta uniformly over the tau. So that is how we get the uniform inference for the local conditional quantile treatment effects with dense covariance. Quickly show you some simulation results. So we simulate the first stage, the IV, by a logistic regression, and we simulate the second stage, the quantile. So within the indicator function, they are just some linear combination of the X. And the X, so the covariance is generated by the normal distribution with mean 0 and a relatively sparse covariance matrix. So in that case, we also generate the local quantile regression function in a linear way, okay? And you can see when the sample size N is relatively large, actually the coverage of the treatment variable, the one with, so when we say the feature, these are the one just X. And sorry, and these non-features are the 0, 1, are the X with 0 coefficients. We can see the coverage for these actually are pretty good, particularly when we have relatively large sample size compared to the dimension here for the P is fixed at 400. In the paper, we also show some other simulation results. Okay, so that's what we do. Okay, so let me quickly discuss some issues here. Okay, so we also show, like in the paper, if we do sample splitting, it can only slightly improve the rate of convergence, but not much. So maybe sample splitting, even though it is very popular these days, in this high-dimensional case, in the inference problem we consider, it's not very effective. And another thing we are very interesting is, which is not discussed in this paper, is the sample selection problem. As we just discussed, like in a general framework, the compliers are usually not observed. So individuals who are assigned to treatment or control, they do necessarily comply with assignment. So there is still a sample selection problem, even with the introduction of the IV. So what can we do? So in that case, then we just want to study the one still when X is high dimensional, but we want to find some bounds for the treatment effects, okay, with endogenous treatment assignment. So just be specific. What is the selection bias problem here? So this is to say wage, again, is the potential outcome, okay? And D is like a job training program, and Z might be lottery, okay? So, but here the wage rates are only observed for those who are employed. And employment status itself is affected by the job training program. So we only observe those people who participate in the job training program and then get a job, okay? So then, there is a selection problem, a sample selection problem. And we show actually, for example, in the very famous job corps experiment, a non-trivial fraction of individuals who are assigned to the job training program did not take the program. In addition, a small fraction of individuals who are assigned to the control group ended up participating in the program. So there's still some selection bias problem, even with the introduction of the IV. So still, we can introduce the binary treatment effects, the binary treatment variable D, the binary IV, and also for this one, we're going to introduce something called the sample selection indicator. It is also binary, I call it S, okay? So we say the outcome variable Y is observed only when the sample selector S is 1 and not observed when S equal to 0, okay? So then in this case, with the introduction of the binary variable S, the observed data are those on the product of S times Y and the selection S, the D, the Z, and a high dimensional covariance X, okay? And we define the sample selection S indexed by the treatment variable D and the IVZ. And also we define the D as indexed by Z, okay? So the causal parameters of interest here is going to be the conditional expectation of S1 minus S0 conditional on C. So C is the compliers, D1 is bigger than D0 group. And this is going to be the treatment effect for compliers at the extensive margin. And we can show this one is point identified. What is this, the meaning of this causal parameter? So like in the job training program, this is the effect of participating in the D, okay? So when D is 1, so this is the effect of participating in the job training program on employment among those compliers. And the second parameter of interest is going to be the expectation of Y1 minus Y0 conditional on S1 equal to S0 equals to 1 for the compliers. So we say this is the treatment effect for the always participating compliers. Okay, so for example, this is the effect of the job training program on the wage rate for those people who always employed and for those people that are in the complier group. Okay, so these two are the parameters of interest. So I'm not going to talk about this one because it is point identified. So I'm going to quickly talk about how to construct the bounds for the second one. So the second one is 0.95. Yes.
So can I just clarify, it's always participating in the sense of participating like in the labor market and being employed, not participating like in the job training program.
That's correct.
Is that
Yes.
fair?
Yeah. Because this is for the compliers already. Yeah.
Yeah.
Okay. So again, we have some assumptions, just like the one I showed you, but here with the introduction of the S, I have some additional assumptions. Okay. So still I have something called exclusion restriction. I have independence. I have treatment monotonicity. I have first stage, and I also have common support. Okay. But the key assumption here is something we call the conditional monotonic selection. This one is to say, we are going to either have the probability that S1 is bigger than equal to S0 conditional X for the compliers to be 1, or we have the probability that S1 smaller than or equal to S0 conditional X and the complier group is equal to 1. So intuitively, this is to assume that all compliers defined by the same covariance X, treatment can either weakly increase their chance of selection into the sample or weakly decrease their chance of selection into the sample. With the help of assumption 2, then we can kind of split the covariance X into 2 parts. So I denote it as X plus and X minus based on these probabilities. Okay. So then
Is this margining out C and D?
that's right, yeah. So then we can show, okay, so quickly show the way to so we can actually construct a bounds, the upper bound and the lower bound for the conditional expectation of the difference of the potential outcome conditional X, the selection for the compliers. This is the causal parameter of interest. And you can see why these 2 papers are connected, because when we construct the bounds, so first of all, it is conditional on the covariance X, and X is high dimensional. And for the bounds, we can see, skip all the details here, but we can actually show the upper bound and the lower bound is a function of the conditional quantiles for the potential outcomes. So evaluated at 1 minus px. Px is the IV propensity score. So we can use the paper I just discussed, the method in that paper to estimate the conditional quantile and then plug in to construct the bounds. That's what we do. So then we can also define some moment functions and show the moment function is a function of these conditional quantiles and the kappa functions in the first paper, and show the average treatment effects for this one is defined, has a bound that the upper bound is the expectation of the moments divided by, sorry, this pi AP is the probability S0 and S1 equals 1 for the compliers. We show that this one can be identified, point identified from the data based on the kappa function and the propensity instrument variable, the propensity score for the instrument variables. So then we can find the upper bound and the lower bound for this based on the moment condition divided by the pi function. Okay, so to construct the moment function, we also need to distinguish 2 cases. The one when X belongs to X plus and the one when the covariance belongs to X minus. Okay. So by doing that, we can find an estimator for the upper bound and also as well as the lower bound, beta U and beta L. Okay, so then you can see we have some first stage parameters for example, for the beta L. I only list the results for beta L here because for the upper bound is the same idea. So we can just, because these moment conditions, some functions of the kappa function as well as the conditional quantiles. So we can use plugin estimator to estimate kappa function, the conditional quantiles, and then we can find our estimator for the moment functions and take the expectation. Okay, so that's the beta L. So the first stage parameters is going to be the selection probability, the tau, the quantile, as well as this kappa function. So similarly, we can find the moment, estimate the moment for the lower bound, as well as the pi function, okay? After that, you find an estimator for beta u and beta L, and then we can talk about do inference for beta L and beta U. But apparently, you can see in this theorem, the moment condition here are not, they are not sensitive to the first stage estimator, these kappas and the conditional quantiles. So we can also derive something called the Newman orthogonal moments based on the original one and show the first stage effects are gonna have any effects on the second stage. By doing that, then we can talk about estimation and inference for beta L and beta U. These are gonna be the estimator for the bounds of the conditional average treatment effects or the average treatment effects for those people who are selected in the data. Okay. So that's the main idea here. So due to the time constraint, I won't go to the details, but that's all I want to discuss today. So thank you very much.
We have about 5 minutes or so for questions.